Thank you very much, John. It's really a pleasure to be here. I appreciate the invitation. It took a long drive to Tampa, Florida to get here because Atlanta is not used to ice storms and snowstorms, and they closed down Atlanta yesterday when I was trying to fly out, so I flew through Detroit. But it's really great to be here, and I look forward to interactions with you both now and especially during the reception. Model-based integrated assessment of food security. I can't really claim to have done all that I'm going to talk about. I'm one of the principals in the AgMIP project, and I'm going to use that as a backdrop of a major global initiative that's going on. It's been going on since 2010. That integrates across disciplines and across different scales of issues related to food production and food security. So I'm going to borrow heavily from some of the things that we've been doing there and talk to you about the use of models in this context. So I'll give a little bit of an introduction about the motivation for the work that we've been doing in AgMIP. I won't talk too much about crop modeling per se, but that has been my major contributions over the years, as John pointed out, and they feed into this as one of the types of models that are broadly used in these kind of assessments. But I'll be basing it, as I said, on the AgMIP effort. I'll be talking about regional integrated assessments and the protocols that we're using for that and the methods. And then the global economic assessments that are going on, and then some of the summary key messages that are coming out of each one of these aspects of the AgMIP program. So the motivation for the AgMIP project is really about feeding 9 billion people by the year 2050. The world's population is increasing, and I know you know all of that because you've got a really good future food program here, but the rising demand for grain with the increased population, been a lot of food and energy price spikes recently. Water scarcity is increasing. Land degradation is occurring in some places where the land is not managed properly. Poverty affects people's access to food. A lot of political instabilities, competition for arable land to expand production. And on top of all of these things, which are really complex in themselves, are the fact that we have weather extremes and climate change that further complicates the issue of providing the food for the future. So the question that we ask is what science is needed, and a lot of things that are being discussed these days are, well, we need to increase production of crops and livestock and fish, and one way to do that is sustainable intensification, and this is being talked about by many of the development agencies and USDA and other national programs. But what technologies and policies are needed, and what investments in research would provide the greatest benefits to society? These aren't easy questions to answer, and they're very complicated by all of those reasons that I gave on the previous slide. And we also feel that there needs to be more engagement with policymakers and stakeholders and more public-private collaboration, because it can't just be the research that does it, and governments can't really provide the increased food and all the infrastructure for providing that to people. It has to be the private sector as well. It's impossible to conduct real experiments to include all of these factors together, and so models are essential tools for studying this. It's not traditional discipline-oriented research is completely inadequate. So a lot of talk is happening these days on the need for transdisciplinary research, and we feel that the AgMIP framework that we've developed and is being used is very much in that spirit, is to have disciplines working together, not just handing some information off to each other, but really trying to understand what's needed and cross-checking the results and so forth. And the last point here is if different models or different climate scenarios are used, you can't really compare results across studies, and you don't really know the reliability or the uncertainty associated with the results. And we found since the early 1990s, when I worked with Cynthia Rosenzweig on one of the first global assessments of climate change impacts on agriculture, we used a particular suite of models for doing that, but now a lot of other studies have been conducted where models developed by other groups, and crop models and economic models are used, and you try to compare them, and they may also be using different scenarios or different climate inputs to these, and so you can't really compare them. So we felt that we need to do a better job in agriculture on understanding the impacts of climate change and looking for ways to adapt to it and increase food security. So I'll talk about the AgMIP project. I've mentioned that already. And our goal in this from the outset has been to substantially advance the scientific capabilities of the agricultural scientists for addressing these complex agriculture and food security issues globally and regionally, particularly related to climate change impacts and adaptation of systems. Since 2010, when it started, we now have about 650 members. Hundreds are engaged in over 31 different activities that are being performed under this umbrella, under this framework of AgMIP that I'll talk about. And it's crop modelers, agronomists, it's economic modelers at different scales, it's hydrologists, it's livestock folks, and information technology specialists that are helping to pull all of this stuff together in this, what we like to call a community of science. In the past, what happened among the different crop modeling groups, and you'll see an example where there are 27 different wheat models. I had no idea that there were 27 different wheat models that have been developed around the world, but there were. Some in the UK, some in the Netherlands and China and Australia and the US, but we didn't really talk to each other except at scientific meetings. We didn't really want to give away our secrets, right? Each one was sort of protecting our own turf and not really collaborating. I think the same was true to some extent with economic modelers. But now they're all working together, comparing their models and looking at ways to improve them. And AgMIP actually stands for Agricultural Model Intercomparison and Improvement Project, so we're actually using that. Part of the motivation for this, we discussed in 2008 when we first, Cynthia Rosenzweig, Jerry Hatfield, myself, and others got together, was the use of multiple models. We looked at what the climate scientists were doing. And I've got a picture here on the bottom of hurricane models that are used to predict the paths of hurricanes. And you see that on the bottom here, you can see that any particular hurricane track model may predict, in this case, the hurricane is going to go over Florida. Others are predicting that it's going more this way. And we're finding, or the climate scientists are finding, that the median of the models is actually the best predictor of the pathway of hurricanes. This is Katrina on the right-hand side here, a major hurricane that devastated New Orleans and caused all the flooding and all there. And the predictions, if you look at the envelope of all of the models that were used, was pretty wide, but the median was spot on as to where it was going. And it at least allowed a lot of people to be evacuated from that area before it hit. and therefore it saved many, many lives. Climate models are the same. The IPCC, of course, has been using 22 or 28 global models of climate change. So we said, okay, what about agricultural models? We knew that there were a dozen or so that had been used in previous climate impact studies. How reliable are these results from the different models, considering that the different ones are used? And would the results be more reliable if we use multiple agricultural models, multiple crop models, multiple livestock models, and economic models? We didn't really know the answer to that. And in fact, a lot of people when we asked this question, they said, no, that's not going to happen because, we have a ways of testing our models using data, and we should be able to have a model that predicts spot on. Well, it didn't turn out that way. I can give you a preview of what the result was. So anyway, we came out of those early discussions with a two-track science approach for the AgMIP project, which has really become a program. In track one, we're talking about the model intercomparison and improvement part, and this would be crop models, agricultural economic models, now livestock models. We're looking at pest and disease models now, just trying to get going on that. And of course, models are central to that in the middle. And then on track two is actually to use these to learn about how to perform these kind of impact assessments and adaptation of climate change impacts in food production and food security and trade and real assessments that are done, and do that both at a regional scale and at regional scales and also at a global scale. So we organized this starting in 2010 by different teams of scientists. We have a climate team, a crop modeling team. Each one of these teams are led by two different people, usually one from the U.S. and these major teams, and one from another country. Economics team. We have an information technology team. And then we have working groups, soils, water resources, livestock and grasslands, pests and diseases that are working together. A number of people in the UK are working on various aspects of these AgMIP teams, working on particular research questions in each area. There are a number of cross-cutting themes like uncertainty, and it's being co-led out of by the UK. Mike Rivington is one of the co-leads on that, and Andy Challoner is another one, for example. Aggregation and scaling, representative agricultural pathways. I'll talk a little bit more about that later. And then we're using these then on the bottom of this slide to have activities for evaluating, comparing, and improving the models, the crop models, economics, and so forth. And then also on assessments of regional and global scale, and we also have crop-specific ones that we're looking at. And we also have capacity building. We're working in developing as well as developing countries on these activities. I'll give you a little flavor of sort of a cross-cutting of these activities. The crop model intercomparison and improvement activities, that's being co-led by Ken Booty at University of Florida, and also Peter Thorburn from CSIRO in Australia. And then I've bolded and put in red the wheat team, because we have also teams for specific crops. Central Asseng, also at University of Florida, and Frank Ewart at Bond University are co-leading this, and I'll show some of their results in just a moment. But we also have teams working on maize, rice, sugarcane, and some other crops. And then finally on this, we have, these are point-based models, and we also are looking at scaling up the predictions of crop production to country or global scales. And we have Joshua Elliott at University of Chicago and Columbia University, and Christoph Müller from Germany, from PIC, working on global gridded crop modeling. And again, multiple crop modeling. And I'll show you why in a few minutes. In fact, this is the paper that many of you may have seen already. It's in Nature Climate Change Journal. It came out just at the end of 2013. And I'll point out some things here. They had wheat, 27 wheat models, and they were comparing them across 4 environments that represent these mega environments of wheat producing areas around the world. These mega environments are actually produced by CIMMYT, and CIMMYT also is involved in this study. But we had areas in the Netherlands, Argentina, India, and Australia, where we compared these models, and the X's on in these diagrams here show the actual production that occurred in these studies. But what this team did, the Centola Asseng and Frank Ewart, sent out the input data for these crop models to all of these 27 teams. The teams had no idea what was actually produced in these areas. It was a blind test, so that they were able to have the weather data, daily weather data for the growing seasons, the planting dates, the fertilizer that was used, the general varieties that were used in those regions, and then the models were run, and the results were sent to Frank Ewart and Centola Asseng, again blind. The first line under that is a box and whisker plot of the results of these 27 models, showing the 10 and 90 percentile levels of the results for the top one here. That's for the Netherlands, yield of over 8 tons at that location, about 8 tons, and then in the other places below. And you can see in the Netherlands, this is the median. The median was pretty close to the prediction of that, and many of these models had never tried to simulate production in the Netherlands at all. Some of them were developed in China or Australia. They hadn't been used in the Netherlands at all, in India. But some of them actually were really wild. They produced very high levels or very low levels. And the story behind this is that the same crop model was not the best one in any of these across all locations, but the median was the best. The median was better across all locations than any single model. And this is true also of the rice model comparison studies that have been done, and the maize models intercomparisons, and that work has just been accepted in a journal for publication as well. So we're finding that the same is true here. It's not very comforting to me, who's worked on crop modeling all along. The crop model that we've developed in DSAT, I was sure it was going to be the best model across all these locations. We've tested it worldwide, and it wasn't bad, but it certainly wasn't the best model in each one of the locations, and it wasn't better than the median across the locations. And the same is true for all the rest of it. Now the bottom here is, once the blind results were sent in, Centola and Frank sent the actual production information to all of the crop modeling teams, all 27 of them. And they were allowed to calibrate or make adjustments based on what they saw the varieties were doing in these different locations, and then see if they could produce better results. And you can see that the uncertainty was reduced a little bit by having some information about the production levels in these locations, but there's still uncertainty there. And so this gives a way of looking at uncertainty in the production as well. So that's just a picture of one of the crop model intercomparisons. And again, what we learned there, the median of the crop model ensembles produced the observed yields better than any single model across all of the locations. And if you have information to improve the model through adjusting what's known about the varieties, it gives you better results. It reduces the uncertainty. The other thing I didn't show here, but in the paper it shows that when they used all these 27 models to do a sensitivity analysis on future climate change conditions with higher CO2s, higher temperatures, and varying rainfall from low to high, the uncertainty increased. And what that tells us is that we need to do a better job of having the models work for future climate conditions where we have higher CO2 and higher temperatures, because the uncertainty increases fairly dramatically when you expose them to the higher temperatures and CO2. And again, the consistent message from all of these models, all of these crops. So the next question we ask is, can these crop models reliably simulate regional and global food productivity? And so we have an effort, and Joshua Elliott at Columbia and University of Chicago is developing a platform for operating multiple models so that we can have more accurate predictions for using in these kind of assessments that I'll talk more about later on. So he asked the question in this particular study, can we use the information about crop productivity across the U.S. to predict the effects of drought on maize production in 2012. And he started this work toward the end of the summer when it was clear that this was one of the major droughts that we've had in the U.S. In the last 50 or 100 years. In fact, it was as bad or worse than the 1988 drought, we felt. In fact, it turned out to be that way. But we didn't know whether these models could actually be used to predict that or not. So he got the records from the U.S. on a county-by-county basis and used that to evaluate the model and to adjust the management, the varieties, the planting date, nitrogen fertilizer, and irrigation, all during this time period based on records, to see if that trend could be predicted using only one model here. In this study, he only used the DSAT maize model. That's the series maize model. And then he used that then before the final USDA projection came out to predict the yield in 2012. And then he published this online, and then several weeks later the USDA came out with its prediction of 7 point, I don't know if that's 6.8, and the final yield that Joshua came out with was 7.75. So it actually predicted that yield pretty well. The other thing he did, and I think you'll find interested when his paper comes out, is that he did a counterfactual. He actually used crop varieties and management from 1988, which is this year here, in 2012, to see if the drought would have been worse then, and how much of the changes in management practices and technology would have influenced the response to yield during that particular drought. So that's and of course in the U.S. we have really good data on these crop production districts, and so that's I think a good indication that when the models are working well, you can use them to predict the area-wide production with care. It took a lot of work to do that. So I want to switch now to some of the integrated assessments that we're doing. Talk a little bit about the regional integrated assessments, and then go to the global. The regional integrated assessments, and I'm showing a handbook that we've created there. We call it a protocol basis for doing that, and it's actually some of this work is supported by UKAID or DFID, and they're funding some of our teams in Sub-Saharan Africa and South Asia for doing this work, and they're doing it on a household basis. So the individual households are surveyed to understand what their production practices are and what their education level is and land holdings and other things. And then the integrated assessment at the regional scale is using a distribution of households. So it doesn't just predict an average household, it predicts a distribution. So that you can get at things like distribution of production, of income, of poverty levels under current and future climate conditions. And it can compare the benefits and trade-offs then among different adaptation options, which includes technologies as well as policies in this. And it uses multiple crop models. We're only using 2 or 3 crop models because we're just getting this started, and the capacity in the regions was only 2 or 3, and we've had to really help them do that. And then the final thing that we're doing here is we're linking it to cost and prices for each region based on these global economic assessments. So the global economic model assessments, I'll talk about that a little bit later, was led by Jerry Nelson out of IFPRI at the time. And then the regional teams are taking those prices that came out of that for putting in as prices for their regional economic analysis, and at least linking them in that way. The globally integrated assessments, I mentioned already that they're using multiple global economic models. There are 10 of them that have been used in the past, and Jerry Nelson led this. And they're also using multiple crop models. At the time that they did this study, they only used, I believe, 2 crop models because they didn't have this platform set up to really do it at the time. And then finally in gray here, we're working now to integrate regional and global more both directions, because we only link from the global to the regional, but really what's happening at the region needs to inform more of what's happening at the global as well. Jerry Nelson stepped down at IFPRI, and so now Keith Wiebe took his place there. He's one of the co-leaders now. We have Keith Wiebe, Hermann Lotzkampen from PIC, Germany, and Dominique van der Minberger from FAO. He's actually moving to GTAP, and then Hans, forgot his last name, John, help me, from the Netherlands. Divide. Anyway, so now there are 4 economists that are co-leading the global economic model for phase 2 effort on this. The regional stuff, we have this framework that I'll talk about just briefly, but on the green here, we're informing the regional economic household stuff by the representative concentration pathways from the AR5 studies IPCC. We have the SSPs, the shared socioeconomic pathways from IPCC that have been developed into some global representative agricultural pathways that then the regional teams are putting together for the regional agricultural development pathways for their regions to sort of put boundaries on what the adaptation options are for particular regions, and it varies quite a bit. And stakeholders have participated quite strongly in discussions about what the agricultural pathways are and what options should be included. And I mentioned already that these prices and costs from the global models are fed into that. But this is basically what you can imagine. The climate data are fed into crop and livestock models at a household level. So all of these households that are in the surveys are modeled, and then these go into to produce a distribution of results. And these distribution of results have been fed into the trade-off analysis model that John Antle has developed. Some of you may be familiar with that. And then this provides the economic, environmental, and social impacts at distribution at the household level from this analysis. And we're using as a basis for this, the teams are using experiments for making sure the crop models, at least 2 crop models are working, sometimes 3 in their area. And they're also using household surveys for getting the practices and the economic and social aspects of that are used in the models. So I've got something here. I'll leave this with you. I don't want to go through all this in detail. And if you're an economist and are interested in this approach for the regional economic analysis, I would encourage you to look up on the web the work by Antle, John Antle. He's now at Oregon State University. But it deals with household livelihood impacts and vulnerability, percent gainers and losers associated with climate change or also adaptation options. So anyway, I won't go into more detail on that because of time. But it also gets at the social aspects of percentage of the population that are at risk of hunger, the percentage that are the percentage change of poverty levels, and it gets at food security as a combination of these indicators that are used to quantify the households. So the teams on the ground that are doing this in Sub-Saharan Africa and South Asia, and of course this is being done in the U.S. and different parts of the country as well, particularly in the Northwest, in a big USDA project. But it's a farming system, and so it's not just crops, but it takes into account the livestock, the fertilizer use, the manure use for the fertilizers, and the labor that's available, and all of the things that are important for household production to produce that. This is the diagram is from Zimbabwe. Patricia Masakati from ICRISAT is leading that team there. This particular diagram on the bottom, the maps are from South Africa, and there the interesting thing is that they have wealthy farmers with large land holding and also small farms with just a few hectares for their farms. And it looks at the impacts and adaptation options for both of those levels. So we had a set of core questions that these teams are addressing. First one is, what's the sensitivity of current agricultural production systems to climate change? And that's taking the current production systems and saying, okay, if we have the current systems in place and we suddenly change climate, what would happen? So that's why we call it the sensitivity. We know that as time goes forward and climate changes, agricultural systems will change as well. And we're at number 2, we're trying to get at that question. What's the impact of climate change on future agricultural production systems? Projecting over time what the production would be if it's sort of business as usual without climate change. And then climate change itself, would be something that would perhaps decrease or could increase production. And then question number 3 about adaptation is with adaptation, how would this recover and then replace some of the losses there? So that's what we're doing there. We set up these core questions and particular simulation experiments to run with the crop, livestock, and economic models for these cases. And I'm going to page through these quickly, but it shows these different teams working together. This is the climate team that provides the daily weather data in the different scenarios consistently across all of the teams in Sub-Saharan Africa and South Asia based on the scenarios from IPCC. 20 GCMs. This shows using RCP 8.5. And so the crop and livestock modelers work closely with the climate folks on this to make sure that everything is consistent with the kind of data that are being provided. There's no funny things happening, and that it can be used to drive the models in a way that they need it. Then the crop and livestock models are adapted to the region. The teams, crop modeling teams on the Sub-Saharan Africa and South Asia, test the models for their conditions and make sure they work. And then they take these farm surveys. Like if in some cases we have, this is 47 farms here, but in some cases we have 250, and in another case I believe 400 farms that have been surveyed, and the models are run for every one of these farms. And we've created IT tools to help the teams do that. So you get a distribution of production changes and, of course, cost and economics associated with that. These are then provided into the economic model as distributions. This just shows a schematic of a landscape, and I don't remember, I think this is in Kenya, showing that the simulation of these different households produces a distribution of yield changes for each crop that are then used in the trade-off analysis model to come up with the overall economic and production and social impacts associated with that. This is a table of one of the teams that comes out. It shows percent gainers, the net loss, a percentage of households that lose, and it's not shown here, but also the poverty, change in poverty level associated with climate change. So this is just to give you, not to show you any specific numbers here, but just to give you a flavor of what our global AgMIP team is helping to create and actually evaluate in a number of different places in Sub-Saharan Africa and South Asia, as well as actually in South America and also in the U.S. So here's some of the key messages that we've gained from that regional integrated assessment. The representative agricultural pathways are very useful for engaging stakeholders throughout the assessment process. So in our very first meetings that we've had in these regions, we've insisted that the teams in Sub-Saharan Africa and South Asia bring in their stakeholders from government agencies, from extension services, other NGOs that would come in and help guide the questions and the studies that would be done during the rest of the project. And that's been really highly valuable. For example, in the last meeting that was held recently, they said they would like to add another question to our set of 3 questions there. And so we'll be doing that in our next phase of the project. we're finding that integration across disciplines is very difficult, but it's essential to do this kind of work. And I think it's more difficult in places that haven't had the culture of working across disciplines. In the U.S., at University of Florida, we work across disciplines all the time. And these institutes, like the food systems groups around, I mean, they provide opportunities for us to work across disciplines. But in these regions throughout the world, we find it's been pretty difficult to do that, but they're now doing that, and they're enjoying this kind of work. The distribution of results provides outputs that are very important to policymakers. They really like not having just one number, but they can see the percentage changes and a distribution. What they wanted in this last workshop was they wanted to include a near-term adaptation core question. Instead of looking at adaptation 25 years from now, what can they do now to begin to adapt? And so they wanted an explicit set of analysis done on the near-term climate conditions. And they're very interested in expanding the work at all the study sites to include more livestock, more diversity of farm enterprises, and pest and diseases. And of course, this is something that we're hoping to do as well. So the global integrated assessments, we have two components of that. One is the gridded crop model intercomparison team, developing and evaluating methods for simulating global crop yields under current and future climate conditions, and with gridded inputs on soil, weather, and management, and multiple crop models. And then we have the global economic modeling team that I've already mentioned, so I'll continue on with that, and 10 global economic models. And this is sort of the schematic of what the team has been doing. Climate scenarios, daily inputs to crop models, primarily now. Representative agricultural pathways, management inputs, the soil inputs, and then the economic models also have their own set of inputs, and they take these results from the crop models, and then the predicted outputs from that. And so the difference in this and what's been done in the past is that this used 10 global economic models, which was quite interesting. And again, using these scenarios from IPCC AR5. And I'll go through this quickly. This is the global gridded crop model work. This shows the result of global gridded using 7 crop models. This was published in PNAS, Rosenzweig, and others came out in 2013. And it shows here for 4 different crops, maize, wheat, rice, and soybean, the predicted, the modeled changes in productivity of these crops under climate change conditions. And you can see some hashes on here. You barely can see it on this scale, but these show for the first time the agreement among models. Where it's hashed, it shows that all the crop models were in agreement in terms of the direction and general magnitude of change that occurred there. And of course, the climate models have been doing this for some time, but this is the first time that was done with the crop models. This shows a band of uncertainty. I mentioned this earlier, I believe, where as we increase temperature and CO2 into the future, the uncertainty gets wider on these models. And so we need to do better about including the effects of temperature and higher temperature and CO2 in the crop models. And work is ongoing to do that. So some of the key messages out of the global work, we found that in contrast to previous assessments, the global gridded crop model results with realistic nitrogen fertilization show steadily decreasing yields. They don't show an increase in yield and then followed by a decrease in yield. They show a steady decreasing yield for wheat and maize in the mid and high latitude regions, even for small and temporary increases. Crops with lower latitudes show greater vulnerability, and this is consistent with some of the earlier assessments that have been done on productivity. And then for the first time, we've been able to show crop model uncertainty on these kind of assessments, and highlighting the need for continuing the rigorous model evaluation and improvement for future studies. And I put Martin Perry and Cynthia Rosenzweig's name here because they're working on a synthesis paper that synthesizes these key messages from these AgMIP studies. I'm going to go through this quickly. The Modeling Climate Change in Agriculture, the Jerry Nelson-led Global Economic Model Comparisons. There's 7 papers in the Journal of Agricultural Economics that have come out, and they're dealing with different aspects of this. And one of the papers that Jerry was author on was, why do these global economic models differ? And I'll show you here that they differ quite a bit. These are the prices that came out of, in this case, only 9 economic models. I think the 10th one didn't have prices involved, but these are the different models across here. You can see the impact model for IFPRI, the Magpie model. That's German, I believe. Anyway, these are the 9 different models, and these are the different crops: wheat, sugar, rice, oilseed, and cereal grain crops combined. And you can see that there's a lot of variability in what the different models predicted under the different scenarios that they produced. It's just a lot of variability. But in general, they all predicted that climate change would exert upward pressure on agricultural prices. It's just that there's a lot of uncertainty, but we didn't know what that uncertainty was before this study. So the key messages here, again, that climate change in the models were consistently showing an upward pressure on agricultural prices. The economic responses reduce yield loss, increase crop area, and reduce consumption. So this also came out of the economic models. And that the economic models differed primarily in the assumptions about the ease with which land use can be converted, the intensification and trade that was in the different crop models, different economic models. So I will close with that, but I wanted to point out, at least from my point of view, that this the AgMIP platform AgMIP project is really a platform for collaboration among disciplines and across the world, really, for producing new science results that are really interesting. That if we didn't have this kind of collaboration, we couldn't have seen these kind of results from the different crop and economic models. And it's very, very important. We don't know yet whether the median from the global economic models is the best answer or not. I'm not sure what you compare it to, like we do with the crop models, but we certainly would like to know about the uncertainty, and it does provide that. And the other take-home message out of this is that there's considerable potential for more advances. We're thinking about new things and new activities that are needed, and we think very important as we continue this. And it's been really exciting to be a part of this and to help guide this. I'm not sure leading it is exactly the right word, but at least helping to guide it and putting operating principles in terms of transparency and openness and proper recognition of contributions across all the groups. So I want to thank you again for allowing me to come here and speak to you about these things, and I appreciate it very much.